Thanks. Is that good? At the outset that the work that I'm talking about today is joint with Aaron Abrams, Noel Brady, Moon Dutton, and Robert Young. So the topic of today's talk is going to be what are called higher divergence functions. But I'm going to start by talking about geodesic divergence, which might be more familiar to people. So consider a metric space with a base point, and consider a pair of geodesics emanating from the base point. Now, let's say you want to get a sense of how quickly these geodesics are moving away from each other. Here's one way that you might do that. Consider the time r points in the two geodesics. So in this picture there, it's gamma 1r and gamma 2r. And the dotted line that you see there is meant to be the sphere of radius r. And consider all paths that connect those 2 points and that lie outside the ball of radius r. Now, I'm going to call such paths r avoidant. And for the rest of the talk, I'm going to adopt the terminology that r avoidant, any object that's r avoidant means it lies outside the ball of radius r. Okay, so if you look at the infimum of the lengths of all such paths that are both r avoidant and that connect the 2 time r points, that gives a measure of how far apart the 2 geodesics are at that particular time. And so to quantify how quickly the geodesics are moving away from each other, one thing you could do is to consider what you get from this by varying r. So more precisely, the divergence of the pair of geodesics, gamma 1 and gamma 2, is a function whose value at r is the infimum of the lengths of these paths that connect the time r points and are avoided. Okay, so this is something that measures the spread of a pair of geodesics in a space. Now, Roushon used this idea of divergence in spaces to get a quasi-isometry invariant for groups. So given a finitely generated group, there's a natural space associated to it, namely the Cayley graph, which is just a graph whose vertices are exactly the elements of the group, and 2 vertices are connected by an edge if they differ by a generator. So there's a finite generating set, and so you get this locally finite graph. And it's a metric space. It's naturally a metric space because you just declare that each edge has length 1. And so you could consider the divergence of geodesics in this space. Now, in order to get something that's an invariant for the group, he considered, rather than considering a pair of geodesics, he considered all pairs at once and sort of looked for the most extreme behavior. So more precisely, here's the definition. Let's denote the sphere of radius r by SR. And so in this formula here, for any pair of points in SR, those are the time r points of some pair of geodesics. And for such a pair, you look at the same thing that we were looking at before, namely the infimum of these lengths. And then you just look at the supremum over all possible pairs. Now notice that there's this extra row that you see here. That's coming from the fact that we're trying to define something that's going to be invariant under quasi-isometry. So a quasi-isometry of a space is allowed to stretch distances by a constant factor, and you're allowed to add a constant term. And so if you want a function that's invariant up to quasi-isometry, you need to be a little more lax, and you need to coarsen your idea of what it means to be avoidant a little bit. But now what we've got here is we've got one of these functions for each row between 0 and 1. And so the divergence of the group is the collection of all of these functions that's parameterized by row. Now, in my definition here, I kind of assume that every pair of points can actually be connected by a path that lies outside the ball. And so I'm just assuming that my group has this property. This property is exactly the property that the group be one-ended, or in other words, be connected at infinity. Okay, so I'm only going to define the divergence for such groups. Okay, so we saw on the previous slide that the divergence is this family of functions that's parameterized by rho. And one needs to say what it means for two families to be equivalent. But once you, there's an appropriate definition, and once you make that definition, quasi-isometric groups have equivalent families as their divergences. Or in other words, div is a quasi-isometry invariant for groups. There's this standard notion of equivalence in geometric group theory that comes up a lot when you study things like Dane functions. You may have seen it before. It's not so important what it actually is. It's an equivalence that, for example, distinguishes between polynomials of different degrees and identifies all possible polynomials of a particular degree, for example. It also distinguishes exponentials of different heights, but identifies exponentials of different bases. Anyway, so roughly the idea is that these two functions asymptotically behave the same. So it would have been nice if, if this family of functions parameterized by rho all had, were all equivalent up to this equivalence. But a priori, that's not necessarily true. This family could have multiple different equivalence classes. And it turns out that there are actually examples where that does occur. But that's not going to occur in any of the examples that I'm going to talk about in this talk. And so for the purposes of this talk, I want to make a definition, which is that the divergence is equivalent to a particular function if that function occurs for all small values of rho. Now remember, rho was kind of the proportion of the ball that you're allowed to dip into. So if you reduce rho, that means you're just allowing more and more paths, and therefore there's a potential of making those infimins smaller. And so delta rho decreases as rho decreases. And so if those functions in the family stabilize after some point, then the divergence is equivalent to that function. Similarly, you can define what it means for the divergence to be bounded above or below by some function. Okay, so this is something that's been around for a while and has been studied in various different cases. So some basic examples are, well, z to the n. If you have any pair of geodesics in z to the n, then then connecting them outside the ball of radius r, as everyone knows, is no harder than going into the ball of radius r. And so the divergence in z to the n is linear. On the other hand, if you have a one-ended hyperbolic group, then geodesics, any pair of geodesics that's not asymptotic diverges exponentially. And so you have that the divergence is actually exponential. So what about for cat0 groups? Well, for a while it was thought that maybe cat0 groups exhibit this dichotomy that's present in, say, symmetric spaces where pairs of geodesics diverge either linearly or exponentially, but you don't see anything in the middle. But Gersten, a while back, gave an example of a cat0 group where the divergence is quadratic. So that means that there exists a pair of geodesics that diverges quadratically. And on the other hand, quadratic is the worst possible behavior in this particular group that you see. And then much more recently, Makura showed that in fact any r to the d can occur as a divergence of a cat0 group. So there's a whole range of behavior that's possible in cat0 groups. Another recent result is on the divergence of the mapping class group. So if G is greater than 1, then the divergence is quadratic, as was shown by both Weierstock and Duchin and Rafi. So there are also some other results that connect divergence to other things that people study. So Gersten and Kapovich studied the divergence in the case of 3 manifold groups. And this is an interesting application because it's a case where the divergence is actually used to characterize graph manifold groups, namely that they're exactly those that, among 3 manifold groups, that have quadratic divergence. And there's some other recent work by Jutu, Moses, and Sapir, in which they characterize linear divergence. So they show that a group has linear divergence if and only if no asymptotic cone has a cut point. and people were independently interested in cut points because they arise in, say, for example, a characterization of relatively hyperbolic groups and things like that. So it's kind of interesting that there are these connections to other group theoretic properties or geometric properties associated with the group. And Drutu, Moses, and Spatzier also investigate div in some other settings. For example, I think lattices and semi-simple Lie groups and some other cases which I haven't actually written here. But anyway, so there are all these interesting properties associated to divergence of geodesics, and so it's natural to ask whether a higher dimensional analog would also yield some interesting properties. So I want to define what the higher dimensional analog of this concept would be. So let me go back to the definition for a minute. So 2 points on the sphere of radius r, that's what we consider when we look at div. And that's the same thing as a 0 sphere on the sphere of radius r. And a path P connecting those 2 points is nothing but a filling of that 0 sphere by a 1 disk. So, and then what do? To compute div, you fill all possible 0 spheres on the sphere of radius r by 1 disks, and look for the worst possible efficient filling. And this is exactly the sort of thing that you do when you look at a filling function, except normally you don't have this additional restriction that these things be avoided. And so you can think of div as a kind of restricted filling function. So a filling function, sometimes called a Dane function or an isoperimetric function, involves exactly this procedure. So you fill some object with some higher dimensional object. And what I mean by fill is that the higher dimensional object has the original object as its boundary. And then you look for the worst possible efficient filling. That gives you a function, and that describes some geometry of the space. Okay, so when you look at it this way, there's a natural way to generalize this to higher dimensions. So for example, you could replace 0 spheres by k-dimensional spheres and 1 disks by k+1 dimensional balls. And Brady and Farb gave a definition along those lines, and their original definition was in the context of Hadamard manifolds. So the definition that I'm about to give today is inspired by their definition, but it's a little different, and here's how. So anybody who's thought about filling functions knows that when you're trying to fill something with something else, there's some choices involved. So a k-dimensional sphere can also be thought of as a k-dimensional cycle. And a k+1 dimensional ball can also be thought of as a k+1 dimensional chain. So rather than thinking of filling k spheres with k+1 balls, you could also think about filling k-dimensional cycles with k+1 dimensional chains. So that would be a homological Dane function, whereas the version where you fill spheres with balls would be the homotopical filling function. And the version that I'm about to give today is the homological one. So you start with a group that's k acyclic at infinity. All this means is that given any k cycle, you are actually going to be able to fill it in an avoidant way. And then you need a space to work with. In the 0-dimensional case, we were working with the Cayley graph of the group. Now we need a space that models the group in some way. So just take the universal cover of a KG1. Okay? You know that's going to have the right properties, the right avoidant filling properties. Okay, and now consider our avoidant Lipschitz k-cycles in this space. Now the Lipschitz part is in order to guarantee that there's a well-defined way of talking about volume. So a Lipschitz function is differentiable almost everywhere, and so it's easy to sort of define a concept of volume for such cycles. And notice that there's this extra condition here. So the reason for that is, one reason for that is that in the previous case, the zero spheres just were on the sphere of radius r. Whereas here, I'm relaxing that a little bit and just saying that the cycles are r avoided. They don't actually have to lie on the sphere of radius r. It's just more convenient to work with a slightly relaxed definition there. But the fact that the 2 points were on the sphere of radius r was a restriction. It prevented the points from being arbitrarily far apart. And so we want some restriction on the spheres now that we're allowing them to be anywhere outside the ball. So they wanted to put some restriction. This actually comes from the original Brady-Farb definition. I'll say a little more about why they chose that particular bound a little later in the talk. But for now, let's just say we're only allowing r avoidance cycles which have volume at most a times r to the k. And then you fill them with rho r avoidant Lipschitz chains. So just as before. This thing is supposed to actually be dipping inside this ball, but I think it doesn't actually look like that. Okay, so then the definition, just to spell it out again, for G, rho, and A as before, the divergence of G is this whole family of functions. This time it's parameterized by two variables, rho and A. And for each, and so it's a supremum over R avoidant K spheres with this restriction on the volume of the efficient rho R avoidant fillings. Again, you need to say what it means for a family of functions of two variables to be equivalent, but there is a reasonable notion with respect to which this is a quasi-isometry invariant. And again, for the purpose of this talk, I'm just going to make this definition. Div is equivalent to a particular function if that function occurs for all small rho and large a. Now, this may seem a little strange, but it turns out that that's exactly the right thing to look at. So it turns out that if you have two things that are quasi-isometric, then they exhibit the same behavior when rho is small and a is large. And so that's the sort of corner of this rho a square that you should be focusing on to get information out of this div definition. Okay. Yeah, so the volume is the integral of, so you have this function that's differentiable almost everywhere. And yeah, so it's the integral of the form that you get. Yeah. Yeah. Yes. So, I mean, so you can put, so in the cases that I'm going to be talking about, you're going to use the cat zero metric that's on the space. Yeah, so you can think of you can put a piecewise metric on the complex piecewise and then use that. Okay. Anyway, so I don't want to go into the technical details of how the volume is defined. But anyway, right. So what I did want to talk about was I mentioned this connection with filling functions before. So when you define the k-dimensional Dane function of a group, you consider k cycles with volume bounded by some number and any chain fillings. And then the Dane function is this function right here. So you're doing the exact same sort of thing, except without the condition that the filling be outside a deleted ball. So there are 2 points I want to make. One is that you can think of these things as Dane functions at infinity. So this is sort of in keeping with the terminology of connectivity at infinity, where you're looking at the connectivity of the space after you delete larger and larger balls. So here you're sort of studying the Dane function when you delete larger and larger balls. Another thing is you need to be a little careful if you're actually trying to compare the Dane function and the divergence function for a particular space. Because notice over here, the Dane function is a function of the boundary volume. So it's the function of the thing that you're trying to fill. Whereas in my definition of divergence, it was actually a function of the radius of the deleted ball. And then we had this condition that the volume is a function, the volume of the thing that you're trying to fill is a function of the radius. So that comes up, for example, when you look at this relation. So the reason why there's this r to the k here is because r to the k is the volume of the cycles that you're trying to fill. Okay, but notice that you do have this relation that's pretty easy to see. The way to see that is, so in order to show that something is a lower bound in the divergence, what do you need to do? You need to exhibit some cycle such that, you know, any filling of that cycle has volume at least this function. Well, if you take a cycle that's very far away from your deleted ball, then the fact that you deleted this ball somewhere out here isn't going to make a difference. The efficient fillings that you're going to see are going to be no different from what you saw when you were just looking at the ordinary Dane function. And so we've exhibited some cycles for which you can do no better than the Dane function, and so the Dane function has to be a lower bound. Okay, so for example, that gives us a very easy way to get a lower bound in the divergence of, say, z to the n, because the homological isoparametric function for z to the n is x to the k plus 1 over k. That's a result of Federer-Fleming. And so that tells you that r to the k plus 1 is a lower bound on the divergence of z to the n. And it turns out that that r to the k is also an upper bound for this divergence. So if you think about that, that's not actually perhaps that surprising. So what does it mean to say that r to the k plus 1 is an upper bound? Or essentially what we're saying here is that the Dane function is an upper bound in the divergence. What we're saying is if you take an avoidant k cycle in z to the n, then it's really no harder to fill it outside the ball than going inside. And it's kind of believable in Euclidean space, particularly if you think about a cycle that's pretty simple. It turns out it's actually a bit tricky to show it in general because you have to consider cycles that might wind around a lot. And you need to know how to sort of fill them outside the sphere. So I want to go over the proof of that. So what does it mean to show that r to the k plus 1 is an upper bound? Well, you start with a Lipschitz k cycle with the right volume. And you want to show that given any such Lipschitz k cycle, there exists some filling whose volume is at most r to the k plus 1. That's what that's what constitutes showing that r to the k plus 1 is an upper bound. So here's how you do that. First, take this k cycle and just scale it down by a factor of r. So since the original thing was bounded by ar to the k and it's this k plus 1 dimensional object, the new thing that you get has volume at most a. So it's some uniformly bounded constant. And now just take any old filling of this cycle. Okay, so take this filling tau prime. Because the volume of the original thing, sigma prime, was uniformly bounded, you also know that the volume of tau prime is uniformly bounded. Okay, but the problem is it's no good just scaling back up tau prime because tau prime may get arbitrarily close to the origin. And what we really want to do is we want to show that we can always avoid a definite proportion of the R ball. So we want to pick some row or show that there exists a row such that we can construct a filling of sigma that's rho R avoided. So, and we don't know that that's going to happen if we just scale back up, scale tau prime back up. So use a little trick that Federer and Fleming actually used in their proof of the isoparametric function. So they have this deformation theorem, and this involves putting a cellular structure on the space. Okay, so in this case, pick a grid, so pick your rho. Rho is the proportion that we're going to avoid eventually. And pick a grid of cubes with side length 2 times rho. And with the additional condition that the center of one of the cubes, the origin is in the center of one of the cubes. So the grid is going to be rho avoidant. So here's the origin, and sort of start with that square and then just continue putting a cell structure on Euclidean space in that way. So here's this grid that's rho avoidant, and the deformation theorem says that you can approximate this cycle, the singular cycle tau prime, with a cellular one that lies in this grid, and when you do that, you don't change the volume by that much. So the new volume, in the theorem, it says that the new volume is a constant multiple of the old volume. Since this was some constant, we just have a new constant here. It's a slight lie to say that this is actually a filling of sigma prime, because when we moved the chain tau prime to make it cellular, we would have also moved its boundary. But it turns out that you can ignore that part, because the sort of extra volume that you get by moving the boundary to make it cellular is also bounded in terms of the volume. It is also a constant multiple of the volume of tau prime. So in the end, what you get here, C is secretly just a uniform constant times B. Okay, but now we've got this nice filling, and it avoids the rho ball centered at the identity. And so when you scale it back up, you get something that avoids the rho R ball. And it's a k plus 1 dimensional object. So when you scale it up, the volume gets multiplied by r to the k plus 1. And so we've produced this filling which satisfies the 2 conditions that we needed. And that shows that r to the k plus 1 is an upper bound for the divergence of z to the n. Okay, so that was an example. Now I want to go back and actually talk about Brady and Farb's original results on this topic. So, or mention some of them at least. So what they did in their paper is compute these divergence functions for some specific Harman manifolds. For example, H2 cross R. They showed that the divergence is exponential, and similarly, a product of hyperbolic spaces has exponential divergence. And notice that the dimensions of the divergences are changing here, and that in each case, it's just 1 less than the rank of the space. So the Euclidean rank of the space. In this case, the rank would be 2. And in this case, when we take a product of k hyperbolic spaces, the rank of that is k minus 1. So another thing they did, and the way, so to show a lower bound on these divergences, they gave a procedure for finding spheres that are hard to fill. And the idea was, if you're in this situation where you're looking at the divergence that's in dimension 1 less than the rank, then there's a way of finding a sphere that's going to be hard to fill by intersecting maximal flats with the sphere of radius r. So let me try to draw a picture in the case of H2 cross r. So, so here's the H2 direction, and here's the r direction. And so there's some maximal flat here. I mean, pick a maximal flat. And so the intersection of the sphere of radius r in the whole space is the sphere of radius r in the maximal flat. So that's F. Now, the volume of that sphere, if we're in dimension k minus 1, if the dimension of this flat is k, then the volume of that sphere is going to be about r to the k minus 1. On the other hand, now notice that, if I want to fill this sphere and I don't have this avoidant condition, then I can just fill it inside the flat very cheaply, namely if the boundary had volume r to the k minus 1, then the filling inside the flat is going to have volume r to the k. But you can't do that because that's not avoidant. The moment you try to fill it outside the ball of radius r, you have to wander off in some negatively curved direction. And that distance is very long. So, and that comes from the fact that, in the zero-dimensional divergence in that sort of transverse direction is exponential. And so the moment you try to fill this avoidantly, you end up with exponential volume. So I think the reason that they chose that particular bound of r to the k on the boundary volumes of cycles was because it sort of captured this interesting phenomenon that you can actually find these hard to fill spheres when the dimension is 1 less than the rank. And then their idea was that once you cross that dimension, you shouldn't be able to find any spheres that are hard to fill. And so they posed a question, which was, by looking at the whole family of div k's, can you detect the rank? I mean, they sort of stated it for symmetric spaces of non-compact type. But of course, you could ask this question more generally. That particular question was resolved by the combined work of Leutzinger and Hindawi. So more precisely, if you look at a symmetric space of non-compact type with rank m, then Leutzinger showed by sort of a method similar to what I just described here. I mean, that's what we used to sort of find the hard to fill spheres. Showed that the m minus 1 dimensional divergence is exponential, and then Hindawi showed that once you cross that dimension, as long as the divergence is actually defined, you get polynomial functions always. So the sense in which the rank of this space is detected is that when you look at the whole family of divergence functions for over all dimensions, there's a sharp drop in the dimension. There's a sharp drop in the divergence once you cross that critical rank. And later on, Wenger showed a similar result for proper co-compact cat zero spaces. So not necessarily this exponential versus polynomial, but just that when you look at the family of divergence functions, you can detect the rank by noticing a change in the values of these divergence functions. And so another space where it would be interesting to think about this sort of thing would be in the mapping class group, because there is this difference between sort of the rank of the mapping class group and the maximum dimension where divergence is actually defined. So it would be interesting to see if this phenomenon holds there, and that's something that we're currently working on. Okay, so for the rest of my talk, I'm going to switch gears a little bit and talk about some results that we have on the divergence functions for right-angled Artin groups. So let me start by actually defining a right-angled Artin group, since that hasn't actually happened yet so far. Okay, so a right-angled Artin group is a group for which there exists a finite presentation in which every relator is a commutator of generators. Okay, and the most common way of specifying such groups is via a defining graph. So if gamma is a defining graph, you define the right-angled Artin group based on gamma to be the group which has one generator for each vertex and one commuting relation for each edge. Okay, so that gives you a presentation for the group. So let's look at some examples. If gamma is the complete graph on n vertices, then what that means is that so you have n generators, and every 2 generators commute, and so you just get z to the n. On the other hand, if you have n vertices and no edges, then you've got n generators and none of them commute, and so you just end up with the free group. So let's see something that's in between those two. Let's say if gamma is a square, then you've got 4 generators. Each generator commutes with its neighbors, the generators corresponding to neighboring vertices, but generators corresponding to opposite sides of a square generate a free group. And so the group as a whole is F2 cross F2. Okay, and the nice thing about right-angled Artin groups is that they're cat0 cube complex groups. And so there's this nice cat0 cube complex on which these groups act geometrically. And so since I'm going to spend some time talking about results on right-angled Artin groups, let me define this complex as it'll come up in the proofs. So this complex is often called the Salvetti complex, and the way you build it up is you just start by building the presentation complex for the group. So what that means is you start with a wedge of circles, one for each generator. So you've got this wedge of circles, and each loop, each circle is labeled by one of the generators of the group. And then you glue in a 2 torus for each edge. So the reason is that, let's say you're trying to build a presentation complex, the next step that you would do after you build this wedge of circles is you would glue in 2 cells corresponding to the relations, and since all we've got is commuting relations, those relations would look something like this. So what you're seeing here is a square with opposite sides identified, so that's a torus. So gluing in one of these squares is like gluing in a 2 torus, and then you just continue in higher dimensions. So if you have a complete subgraph on n vertices, then you glue in an n torus, and faces of this n torus are going to have copies that you already glued in previous steps, and so you just identify those faces with tori that already exist. So you've built up this space. Now look at its universal cover. The space itself is a Ka gamma 1, and it's easy to see, because after all we built this by gluing tori, it's easy to see that what you get is a cube complex. And in fact, it's a cat0 space. But I'm not going to talk about why that's true. Okay, so it's this complex, and this is the complex that we're actually going to be looking at fillings of cycles and with chains in. So in order to actually do that, we need to know when it's actually possible to fill a K cycle with a K plus 1 chain, or in other words, we need to know when this space is actually going to be K acyclic at infinity. And that was something that comes from some work of Brady and Meyer. So it turns out that you can read off whether the space is K acyclic at infinity just by looking at links of this complex. So if the links are K acyclic, then the group, or in other words, the space, is also K acyclic at infinity. And that's when you know that the divergences are defined. And in fact, detecting whether these links are K acyclic is something that you can just do, is something that depends just on the graph. So you can look at the graph and decide whether or not this condition is satisfied. Okay, so I'm going to focus on groups where this is actually defined. The divergence is actually defined. And this is our result. So for groups, for right-angled Artin groups A gamma, where the divergence, the k-dimensional divergence is actually defined, it's always between r to the k plus 1 and r to the 2k plus 2. This lower bound comes from the fact that the Dane function of these groups is the same as the Dane function for Euclidean space. So that's sort of the same kind of argument that I gave before for Euclidean space. Okay, so these divergences are always between those two functions, and those bounds are sharp. So we already saw the lower bound because there exist groups, namely z to the n, abelian groups, for which the divergence is actually this function right here. And on the other hand, we construct examples of groups which attain the other end of the spectrum. So there exist graphs, gamma k, for which the k-dimensional divergence is actually out of the 2k plus 2. Now, it's also an interesting question, so what happens in between? Is it possible that those are the only two things that occur, or, can you say in terms of the graph what you're going to get, well, first of all, can you say what functions in between occur, and, once you know that, can you say in terms of the graph what function that you're actually going to get? So that's a pretty interesting question, and so we can say something in the case k equals 0 for divergence of geodesics, and that's a result that was also that also appeared in the paper of Berstock and Charney. They sort of came to it in a different context, not in the context of higher divergence functions. But anyway, so the result is that if the group is a non-trivial direct product, then the divergence is linear, and if it's not a non-trivial direct product, then it's quadratic, and nothing else in between occurs. That's not going to be true in general for higher divergence. In fact, for one-dimensional divergence, we do actually have an example where we get a function in between the two bounds. But we don't know anything more about that, about the behavior that occurs there. Okay, so I want to talk a little bit about the general upper bound of r to the 2k plus 2, because the technique that we use there ends up being useful in some other settings as well. So let me start by giving an outline of the proof of the case when, the proof of the general upper bound of r to the 2k plus 2. Okay, so again, what do we want to do to prove the upper bound? We want to start with an avoidant k-cycle, and we want to produce a filling of this k-cycle whose volume is about r to the 2k plus 2. Now, unlike in the Euclidean case, there's no sort of reverse scaling that we can do, because these right-angle Artin groups have a lot of branching. And so you can't just scale back and do some trick in a bounded ball and then scale back up. So we need to use a slightly different technique. And here's what we're going to do. First, start with any efficient filling that's guaranteed by the Dayton function. So we have some control on its volume. But the problem is this filling is not going to, in general, is not going to be avoidant. So we need to find a way to modify it without changing its volume as little as possible. So the idea is to push the filling outside the ball using what I call a retraction from k gamma to the exterior of the r-dimensional ball. Now, the reason that's in quotes is that you know that there can't actually be a retraction from the interior of a ball to the outside. So that's necessarily going to have some singularities. And then finally, we want to define this map in such a way that doing that does not change the volume too much. Okay, so I want to actually define what this so-called retraction is. And as I mentioned before, it has to have some singularities. So in fact, every vortex is going to be a singularity. Every vortex inside the ball of radius r is going to be a singularity. So we define this new space, which is going to be the domain of the pushing map. And so here's how it's defined. Just start with the original complex, k gamma. Remember, this was a complex that we built out of cubes. Okay? And then delete the 1/4 neighborhoods in the L1 metric of the vertices in the interior of the ball. Okay? We don't care about the exterior of the ball because, after all, we're trying to come up with this map as a way to push things from inside the ball to the outside. So the map's just going to be the identity outside the ball, and inside the ball, it's going to be defined on the space with vertices removed. So let's see what that looks like. Within a particular cube, you see something like this. And you get an induced cellular structure on the nu complex. So there are two types of cells in the nu complex, right? There are the original cells that are truncated. So here's a truncated one-dimensional cell, and the pink thing is a truncated two-dimensional cell. And then you've got things that we call link cells. So a link cell, an example of a link cell is this diagonal cell here. So what we're doing is deleting a neighborhood of the vertices, and so sort of the slices are going to give the link cells because they lie in the link of that vertex. Okay, so that's the space, and we've got this cell structure on it. Now let's define the map. The map goes from Kr to the exterior of the ball of radius r in the original space. And as I said before, it's just the identity outside the ball of radius r. We need to say what it does to the interior of the ball. So let's start with the truncated one cells, the truncated original one cells. Now, each truncated original one cell has some label on it because originally it came from some loop which was labeled by a generator. So what we want to do to this one cell is sort of just keep pushing it out until it hits the sphere of radius r. But because these groups have a lot of branching, we need to decide where we're going to push it. We do want to push this whole edge and collapse it down to one point, but where should we send it? Well, that's where this label comes in. I mean, it's just a choice that we're making. So one possible choice of place to push it is just keep following the standard geodesic defined by that generator. So just, in other words, at each vertex you have a choice, just pick the choice that has the same label as your original label. So that's a unique way to arrive at the sphere of radius r. Once you get there, you stop. Okay? So in this picture, you have this you have these four truncated one cells, and they each know where to go just based on what label they have. Okay, and you do this for all the truncated one cells in the whole space. And now, everything else is determined by what we just did. So, for example, let's look at some link cells. Any link cell, say this diagonal one right here, its endpoints already have destinations on the sphere of radius r. Okay, so now you can just extend linearly over that link cell. And then the same with this other one. And so this whole green square just goes to a loop on the sphere of radius r, and in fact it's a degenerate loop because there are only two points. I mean, the image of this set of 4 points here is 2 points on the sphere of radius r. So you just have this thing that maps back and forth along those lines. Okay, so having defined the map on all link cells, there's no choice. I mean, there is some choice, but it's clear what to do on the interior of truncated two-dimensional cells because we already know where to map this boundary. And so we just extend linearly over that 2 cell and collapse it onto some lower dimensional thing on the sphere of radius r. So in this picture, it looks like there's some space in between, but that's just so that you can see what's going on. Actually, all of this is just mapped to one line. And so the 2 cells that you see here are just going to map to degenerate 2 cells up here. So they're not going to contribute to the volume when you sort of compose this with some chain. Okay, so that's the map. Anyway, the point is, so if you didn't follow the details of this map, it doesn't matter. The main point that's important is that if you go through the definition carefully, you can see that this map that we've just defined is a Lipschitz map with Lipschitz constant on the order of r. Okay, and that's going to be the point that's important for estimating volumes. Okay, so let's go back to the proof and just see how the whole thing fits together. I'm going to try to illustrate it on the side here using a 0 cycle as my boundary. Remember, the 0-dimensional case was a little different because we didn't have this volume condition. But the rest of the proof kind of follows the same idea. So we've got this R-avoidant case cycle which is allowable. And we're trying to find an avoidant filling of it. So, as I said before, the first step is to find any old filling. Now, this isn't a very interesting example because it's all within one flat. So, here, this geodesic might actually sort of have more turns and pass through many different flats. But this is going to be enough to sort of see the picture of what's going on. So you take this filling, and you want to hit it with this pushing map. But this pushing map that I just defined had some singularities. Namely, it wasn't defined in neighborhoods of the vertices. So we first need to perturb it off of the vertices. So I've perturbed it by pushing it into the link of each vertex that it encounters. And the links are sort of uniformly bounded in size, and so this can be achieved by some Lipschitz map, whose Lipschitz constant is uniformly bounded just in terms of the graph defining the group. Okay, and now we're in a position to apply the pushing map, so let's apply it. I'm going to do it in two steps. So over here, what's happened is that the truncated original cells have been sent to points, that point and that point. And then the linked cells get sent to large-scaled copies of themselves. And so those are the ones that are going to be contributing to most of the volume of the pushed thing. Okay, so once you're done, you've got lots of copies, large-scale copies of the linked cells and some lower dimensional stuff. Okay, but the important thing is that the pushing map has Lipschitz constant on the order of R. And so we've taken this tau, perturbed it, and pushed it. It's a k plus one-dimensional object being modified by some Lipschitz maps. And so its volume changes by something like the Lipschitz constant to the power k plus 1. And that's where this upper bound of 2k plus 2 comes from. Okay, so the reason I kind of spent some time on this is that it turns out that this is useful in other settings as well. I mean, certainly you can use it to modify fillings in other cat0 cube complexes. But in fact, we were also able to use a similar kind of pushing map to study the divergence, at least the one-dimensional divergence in the mapping class group. So there we were working with a presentation complex, and there you don't actually just have cubes, because the mapping class group has relations other than commuting relations. But it's still possible to sort of use the same kind of idea, to produce these avoidant fillings. And it turns out that the upper bound that we get up here out of the fourth is the same as what we got in the right angle Artin group's case for that dimension. So that was one setting in which we were able to do it. And in fact, we're working on the higher dimensional case for mapping class groups right now. But another interesting application was the case of Dane functions for what are called Besvina-Brady groups. So let me quickly define Besvina-Brady groups. So there are a class of groups that are subgroups of right-angled Artin groups. And they're exactly kernels of homomorphisms. So if you have a right-angled Artin group, you can just define a homomorphism where each generator maps to 1. And the kernel of such a homomorphism is a Besvina-Brady group associated with A gamma. So these groups have lots of interesting properties. Let me just mention what's relevant to this filling function stuff. So Dyson showed that if you look at the one-dimensional Dane function of such a group, then that's almost that's at most x to the fourth for any defining graph. And on the other hand, Brady showed that there are actually examples where the Dane function is x to the fourth. Okay, so what we prove is a higher dimensional analog of that theorem, the combined theorems of Dyson and Brady. So the theorem is if you have a Besvina-Brady group of type fk plus 1, so don't worry about what that is, it's just a condition that you need to actually be able to define the k-dimensional Dane function, then it's at most r to the 2k plus 2 over k, which in k equals 1 reduces to Dyson's result. And on the other hand, these bounds are sharp. So there exist best Wiener-Brady groups for which the lower bound is actually the same as that upper bound. So these we just construct, we construct an explicit family. And it actually turns out that this is related to showing the sharpness of the upper bound for the divergence functions. But I'm not going to have time to talk about that. What I do want to talk about is this upper bound, because this idea of a pushing map does actually help in this setting as well. So how do we get an upper bound? Well, first let's talk about what space it is that we're actually trying to fill in. Well, if you have this map, remember, these groups were kernels of this map right here. So A gamma to Z, where each generator goes to 1. Okay, so that map induces a function on this complex K gamma. So you can just sort of, the sort of edges of this complex is the Cayley graph of the group. So that knows where to go. And then you just extend linearly to higher dimensional cells. Okay, so you've got this height function on K gamma. And it turns out that the best Wiener-Brady group acts geometrically on the level set, on the 0 level set. And so that's the space where we want to look at cycles. This time we don't need any avoidant condition. We're just looking at the ordinary gain function of these groups. So we take cycles that are in the level set, we want to fill them in the level set, and we want to see, and we want to show that any cycle has a filling whose volume is at most this function. Okay, so here's the idea. Use pushing again. Okay, so the ambient complex is this cat 0 space. So if I have a cycle, actually maybe I should go down to this lower thing. Let's just give the idea here. If you have a cycle at level 0, then you can fill it in the ambient cat 0 space. You know how to do that efficiently. And now push, this time not to the ball of not out of the ball of radius r, but towards the 0 level set. So the pushing map is going to be different. It's defined in a very similar way, but instead of going from the interior of a ball to the outside, it goes from points at non-zero height to the 0 level set. So what you can do is take your cycle, fill it in the ambient cat 0 space, perturb off of the vertices at non-zero height, and then apply this pushing map. Once you apply the pushing map, you end up with a filling of the cycle that's in the 0 level set. But you also have a similar condition on the, you also have a similar control on the Lipschitz constant of this map. So you can show that by pushing it into the 0 level set, you don't actually change the volume too much, and that's what gives the upper bound. So that was just the idea of how to use this pushing map in settings other than the divergence functions case. And I'll stop with that. Yeah. Yeah. Are you asking about Dane functions or divergence? Yeah. So there's a yeah. So in dimension 3 and higher, so if the boundary has dimension 3 or more, then if you're trying to fill in a simply connected space, the functions are not different. Robert Young has an example that shows that they can actually be different in dimension 2. Yeah. And I think they can be different in dimension 1 as well. But that's slipping my mind right now. In divergence? Oh, gap in higher dimensions for Dane functions? I don't know of any gaps because there was these results of Brady and Forrester that show that there aren't any gaps that are analogous to that gap from quadratic to linear. So they produce the higher dimensional version of that would have been, there was a question of whether there was a gap from 1 to 1 plus 1 over n, and then they produced these examples which filled in that gap. So I'm not aware of any other gaps in higher dimensions.